is a scalar quantity. Electric flux is a scalar quantity, whereas electric flux density is a vector quantity. So when you talk about electric flux, as I said, is a number of field lines that crosses a given surface. Okay. So ideally, we all know when you take a positive charge, the flux or the field lines move from or moves away. If you take isolated positive charge, always the flux or the field lines are moving away. But when you take a negative charge, the flux or the field lines are always receiving the charges. So if you take a pair of a positive and negative charge, that means always the flux will move from the positive to that of the negative. Okay, likewise, if we take an isolated positive charge, then the flux is moving away from the charges. And likewise, if we take isolated negative charge, instead of the arrows to point away, it will be pointing towards the charge, meaning for flux, always the charge is moving towards the charge, that negative charge. Okay. Now to find the charge based on the, to find the flux based on the charge is given by the charge of that particle you are talking about. Remember, have you done Gauss law? Please, have you heard of Gauss law before?
So we have heard it, but
Madam Felicia, I was expecting
yes,
to
sir.
say it. So what is
Oh
Gauss law?
yes, we have heard it. Could you say the mechanic was a bit of question?
Because what me and I'm expecting you to
So
know.
me can't answer what me. Because
If
see
you
a
are
pan, there'll be some pan there. Trying out with me, but my cat was this year. David, make a cap bomb. The army will feel me, yep. So they'll have,
okay. Ideally, you can say Gauss law. Let's take it in this angle. Assuming we are having an enclosed surface, right? And that enclosed surface is filled with some charges. Okay, so it means you know the quantity of charge in that room. It means if you want to know the field lines or the number, the field lines or the flux leaving that enclosed surface is directly proportional to the quantity of the charge in that enclosed surface. Okay, and that's basically what Gauss law talks about. So if you want to find the flux, it's directly proportional to the charges within that enclosed surface. So mathematically, they say the flux is given by, or the flux is equal to the charge, and that's what we are seeing in equation 2.14. Please, I hope I'm not confusing anyone.
No,
Sir, please
sir.
come again.
I said, I hope I'm not confusing anyone.
Sir, please come again. With the Gauss
Come
law.
again from where? The flux or the Gauss law?
Gauss law.
Okay. I'm trying to say, if we talk about Gauss law, all what Gauss law talks about it, assuming we have an enclosed surface, so we can think of anything, whether a bus, right? And in that bus, we are having some kind of charges in that bus. Okay. Then if we are talking about the flux leaving the bus, right, then it's proportional to the quantity of the charges in that bus. So that if we have a bus and the bus is having charges of, let's say, 10 coulombs, it means the flux leaving that bus is equivalent to 5 coulombs. Is it clear now?
So you said that it's proportional to the flux leaving, but if the number of charges is 10 and the flux leaving is 5, won't that be half?
No. If it happened that way, then means that's not the entire flux. That Gauss law doesn't hold.
Okay, so that means that if it's 10 in 10 columns, then the flux leaving should also be 10, right?
Yes, it should be equivalent to 10 coulombs.
Okay. Okay.
But also we take into consideration the cross-section area as where this flux is crossing. I hope it's clear.
Yes, sir. It's clear.
Okay. So assuming, okay, given a vector field A continuous in a region containing the smooth surface S, we define the surface integral or the flux of A through S. So assuming we are having this surface, right? Let me take Madam Felicia Daroma. I know how to use the markers. So assuming we take this surface, right, as our S, okay, and we are saying this surface, we are having a flux leaving only this portion. Okay, how do you define, oh, why? How do you define the flux leaving this area? Oh, why is this thing? Why did it? So we have a flux which is within this whole surface. The flux is just moving through only this portion within the whole area. And we want to know the flux passing. So assuming we have a bus, right? And in the bus, we have a certain number of flux in there, charges in there. And the flux leaving, you know, you've just cut a little portion of the bus, right? The topmost of the bus, a little portion, instead of the whole top. And want to know the flux leaving that small portion. How will you find it? Okay, because this time around, it's not the entire thing that the flux is passing through. So how do we get the flux that passes through just that small area? And it's given by the integral of the surface area, that's the area which the flux is passing. Then you have your A equals theta. And this is the Gauss law, the integral for version of the Gauss law. So we've not changed anything. I know you did Gauss law in second year, electricity and magnetism. You were treated with this. So this equation is not something new, or it's not something you've not seen before. Okay. But the only thing that is introduced is the unit vector. That's the direction. But even with that one, we don't really pay much attention, because if you want you to go ahead and specify, we'll give you the coordinate. But as it stands, at this level, we don't really bother you with the units, normal, tangential to all those kind of things. I hope it's clear.
Yes, sir.
Okay. So at the end of the day, the Gauss law is stated as this. That's for the flux is given as this. So the integral of the cross-sectional surface times the area, the vector flow times the ds, that's the surface. But then I know you know the meaning, or you understand any integral where we have a circle within it. You understand that, right? That if you integrate something and you have it this way, or you integrate something and you have it this way, or you integrate it and you have something like this. I hope you understand it.
No, I don't. We have seen it,
Say
but
wait there, yeah, me na me can no. Say wait
I,
there, yeah,
I,
me.
I've seen it. I've seen it, but I always think it's just integral, since the same integral now. So
Okay.
the same differential now, and integral now. So
Okay, so if you have an integral and you have a circle within it, it means whatever you are integrating or whatever you are paying attention to is within a closed loop. Means it's within a certain circle or a certain spherical shape. Okay. And if you see it in this way, it means whatever you are integrating is around or goes around a square or a rectangular shape thing. Likewise, if you see this in a triangular shape thing. Money contour. Oh, sorry, I'm not sure somewhere. Sorry.
Sir, where would you?
Now, Madam Bishop, I know if you've done a travel castle,
oh, so yeah, you know, be some mamma say, say, I don't know those and any nana yamaka.
So if you see anything like this, it means we are integrating over some closed loop. And hence, as we said, for God's law is for any enclosed surface. That's why we have it in a closed loop, so that it tells you that whatever you are dealing with is within a closed loop. So, for example, even within this surface, we are dealing with this enclosed loop, okay, and that's what you are dealing with. I hope it's clear.
Sir,
Yes.
please, the upper limit, there's a square there. Is it a symbol? And if it's a symbol,
Ideally, if the question is given to give you the limit, what is there? Just the general expression. So this is not really important. Don't pay attention to it. That's why you have the closed surface and you have the surface here giving us S. Okay, so assuming we must specify about the area, then means we give you the area from let's say 0 to pi or 0 to pi on 2. But if you have it this way and you have the S, we are telling that it's over a closed surface, the surface S. Okay, so this one doesn't really matter. I think if you use the normal integral sign in Word, it has to give you the limits. That's why it's there. But then, as far as God's law is concerned, if you are stating it, there's no need for you to bring the box. If you do the closed loop integration, you bring your surface area, you are good to go.
Okay, thank you, sir.
All right. Then move on to electric field intensity. Mr. Ibrahim, I guess you are back. Okay. So if you are talking about electric field intensity, electric flux density, because you said electric flux is a scalar quantity, whereas the electric flux density is a vector quantity. So it means when you are dealing with the flux density, always you also pay attention to the direction. Pay attention to the direction, and direction whether it's in the Cartesian, the spherical, or the cylindrical system. Okay. If in the neighborhood of the elemental surface, the S is in figure 2.7, the lines of flux have the direction of the unit vector AN, and the amount of flux that's the far is versus the differential area ds, which is normal to AN. Then the electric flux density at P is given us. So now we are still dealing with this, right? But this time around, you see our interest is also in the direction at which this flux is moving to. Okay. And then so you have to pay attention to the vector, the unit vector direction, which is the AN. As I said, the flux, we don't really care about the direction, but then because it's a scalar quantity about the flux density, you have to take into consideration the flux direction. Okay, which is given as the differential of that of the flux with respect to the area, then the direction at which the flux is moving to. Whether it's moving perpendicular to the surface, parallel to the surface, or it's inclined to a certain angle to the surface. I hope you are clear. Any question? Okay. So this is basically the electric flux density that you need to know. And if you want to find the relationship between flux density and electric flux, it's given by this. Likewise, if you want to find the relationship between electric flux density and electric field intensity, okay, where we know electric field intensity talks, I guess you are aware that electric field intensity is a vector quantity. Hello.
Mama ni naila.
Kelly, we are more than you. Please,
So
I
they
guess
go right.
electric field intensity is a vector quantity. Okay, it's a vector quantity. Likewise, it's electric flux density, as we just stated, and it's related to the electric field intensity as the permittivity not times that of electric field intensity. Why? Because if you are talking about electric field intensity, it's telling us the intense or the strength or the force that is being exerted on any object, which is
You're right, why? You're right, Madam Fisher, you're right.
which is placed in the region of electric field, right?
Where were you?
If this field is having a flux passing through that point, that means at any point you can find the flux density at any given point within that field. And then it's related to permittivity notes, where the permittivity notes is telling us the permittivity of that field that you are dealing with. So if you are talking about in free space, you have the permittivities. If you are talking about the electric field within vacuum, we have it. Electric field in the field intensity within let's say water, a region where we have water, and we say we are fine, electric field intensity is found within that place. It means the permittivity at that point also differs. Okay, so the region we are talking about, the region which is in respect to, or the field at which we are studying, determine the permittivity node that we are dealing with. And if you know the field intensity at that point, means you can also find the flux density at any given point within that field. And that's the relationship between the field intensity and the flux density. Any question? Okay. Then you can also move on and talk about the net charge in a region. So assume you have a certain region and you want to find the net charge within that region. And it's given by, so if you are talking about, let me not just brush on one customer. When charge is distributed throughout a specified volume, each charge element contributes to the electric field at an internal point. A summation or integration is then required to obtain the total electric field. So if you are talking about a certain volume and want to find the intensity or the intensity of the electric field, okay, you can also do that. How? By integrating or differentiating at that volume that we are dealing with, then we just sum them up. Okay. And you know, even though electric charge in its smallest division is found to be an electron or proton, it is useful to consider continuous, in fact, differentiable charge distributions and to define a charge density by. So if I find a charge density, that's the rho v, okay, where the rho v is talking about the charge density, but then in the volume form. Okay, so assuming we have, as I first used as an example, we have a box, and this box is containing charges. Okay, and we want to find the net charge within that box. Okay, it means if you know the number of charges in there, you can find them individually, and after that, we sum them up. Likewise, we can integrate it and then we find the total charge within that volume. And it's giving us what we are seeing over here. Okay. Are we good, or there is any question? Because we did this in electricity and magnetism, that's why I don't want to go deeper. So from this, we can make the Q the subject so that the Q will be equal to rho v dV. Okay. So that now this is the charge density and this is the volume. So if you want to find the total charge, it's a matter of just integrating each portion so that this will cancel out of the G. Then our charge will then be giving us the integral of the volume that we are dealing with and the rho, that is the charge density with respect to the volume you are dealing with. Are we good? Yes, we are good because you treated this in electromagnetism. Then go to Gauss law itself. So Gauss law, I think we've defined that already. That the total flux through the equal surface is equal to the total on net charge enclosed by that surface, which you said the charge is equal to the Q naught. And likewise, if you want to find based on the flux density, it's also understandable, which is the flux density times that of the integral of the surface to that of the flux density also give the total charge enclosed within that surface. I hope you are good. I'm just brushing through because I know we've done this. We've done this electricity and magnetism, and I've also spoke about it already. That's why I'm just brushing through. Then you can go on to special Gaussian surfaces. Special Gaussian surface. So as I said, if you are dealing with a Gaussian surface, and this surface, we have to make sure that, or you have to have some clues in it, that whenever you hear a Gaussian surface, you should know that that surface is always an enclosed surface. Okay, that surface is always enclosed. And also at each point of the surface, the flux density is either normal or tangential to the surface. Okay, so if you take any surface, right, and you are saying it's a Gaussian surface, then at each point, the surface is either normal or tangential to the surface. Okay, because when they are parallel, I don't know, the flux passing through is zero. And also, you have to also understand the point that the flux density is sectionally constant over that part of the surface where D is normal. So if you take the flux and the surface, the D sectional is always constant at any point. Why? Because if you take the bus and you say within the bus, the field, the electric field intensity or the flux intensity at any point is the same. That means even under the bus to the topmost of the bus, the charges between there or the flux density between these 2 points should be the same. Why? Because the total bus is having the total flux density distributed throughout the entire thing. So at any point within that same enclosed surface, they have the same charges or they have the same flux density. I hope it's clear. Please, I hope it's clear.
Yes, sir.
Okay. Then we'll go on to the relationship between D and E, and we've already established it where we say the D is equal to permittivity times that of E. And then you can go ahead and prove it, which I don't do that because I don't want to bother you and I don't also want to bother myself. So this is the relationship between them. Okay. And what we just need to know is that if you are talking about electric field intensity, the field we are dealing with also have impacts on the force experienced within that field. Okay, for example, if someone is running on a bare land, the kind of force the person needs to push itself will be lesser as compared to someone running in water. Okay, so the field at which the charge finds itself also play a very important role. But then the flux density is just the movement of the field lines from one point to another. And that's why when you are relating the flux density to that of the electric field intensity, you always multiply the electric field intensity with permittivity naught, which talks about the field that you are dealing with. It talks about the field you are dealing with. Okay. So that also brings us to what we have here. This is not something. Yes, let me just mention it. So example, we have this volume, right? And we have volume 2. Now, if you want to find the total flux within this volume 1, that's if you want to find the flux within this volume, okay. It's just a matter of summing the entire charges within this volume, and that should give you the amount of charges within that, and that will give you a fair idea about the flux density. So in this case, the total charge here will be, we have positive n nanocoulomb plus I have negative 5 nanocoulomb as well. So that if you want to find the total charge within this flux, it's going to be positive 5 nanocoulomb. I hope it's clear. So
Hello, sir.
Yes.
What are technically has reduced from positive 10 nanocoulomb plus negative 5 nanocoulomb to positive 5 nanocoulomb. What does this simply mean?
It means when it comes to the field you are dealing with, you have
Yes.
positive 10 charges and you have negative 5 charges. Okay.
Okay.
But we all know if you want to find the total charge within the surface, always the negative absorbs and the positive push away.
Okay.
So the negative always neutralizes the amount of positive charges you are having. So if the negative overshadow the positive, it means that field is accepting charges into itself.
Yeah.
Okay. Likewise, if you get positive, it means the field is eliminating positive charges.
It's accepting more charges.
Yes, if it's negative, it's accept, but if it's positive, it's report, it's pushing the charges away to infinity.
Okay.
Yes.
Okay.
So likewise here, this negative 5 will neutralize half of what we have over here. Okay. So that at the end of the day, this one is pushing all the 10 away, but this one is accepting 5 of them. After taking 5, the remaining 5 will be the one that will be distributed in this area.
The surface will have a net charge of plus 5 nanocoulomb.
Yes.
Okay. All right.
Likewise, if we come to the volume 2, this volume 2 is a neutral field. Why? Because we don't have any charge here, but then we have a charge that is treated outside. So this Gaussian surface is a neutral field, which has no charges. It means at the end of the day, it does not have any flux density within its region.
Okay. All right. Thank you, sir.
You're welcome. So that is that for that. They said find the charge in the volume defined by. Now you see, now they're giving you the limits. Now they say the volume is defined by 1 and 2. Okay. And they say it's in the spherical coordinate system. Now, I hope you've not forgotten what we treated before. The cylindrical and spherical and Cartesian. Okay. And now they said the flux density is given by this. Okay. 5 cos squared theta over r exponent 4. Okay. And now we also saw earlier, where is it? Let me go there before you say you did it, so I didn't mention it. We also saw earlier that if you want to find the net charge, it's given by this. Okay. Now we know the rule. So you just substitute the rule there, then you put in the limits. I hope you are good. So that when you come here, now the rule is given in the question as this. Okay. And we also know that our Q is given by this. Okay. But then when you are dealing with spherical coordinate system, we mentioned that we have triple differential where one has to talk about the phi, one has to talk about the theta, and one has to talk about the r. I hope you've not forgotten that when you are dealing with volume, the spherical coordinate system, when you're dealing with volume, we said for the spherical coordinate system is given by triple integral of r squared sine theta dr d theta the far. Where if you so you can say the differential the v, the spherical coordinate system is equal to r squared sine theta the r the theta the far. I hope you've not forgotten this when we are dealing with the spherical coordinate system, then the v.
Yes, sir.
Okay, so likewise the same thing. Now in the question they said in the spherical coordinate system, so you code the volume because you are finding the charge that is enclosed within that volume. Okay, so that this time around we want to find the charge, which is the Q. You as rho dv. Now the rho has been given, so you just have to substitute in there that your Q is given us. Now the integral is with respect to that of the r, the theta, and the phi. So you have to make it 3 times. You integrate it 3 times. So the first one has to do with the phi. And when we are talking about that, I said phi has to do with what? 0 to 2 pi. I hope you've not forgotten the limits. You say we are aware, but you have to revisit it. 0 to 2
And just
pi.
walking.
Then you have your integral of that of the phi over there.
And then they may not done.
And the water.
Oh yes.
Then that's of the theta. And we said the limit for theta is also from 0 to pi. So if we are after today's lesson, go back and read. And now the theta is not just theta, but it's sine theta the theta. So you have what? Sine
theta
the theta. Okay. Then move on to the. Oh, sorry. I should have brought. I will come back to that. When we come up to the r, where the r, we said the limit is what? From 1 to 2. You have our 1 here, you have our 2 here, and it's r squared the r. Okay. Then we can put this in a square bracket. Then we bring the volume that was given in the question, which is 5 cos squared 5 all over r exponent 4. Okay. So with this, you can put the r factor over here. Then you can put the cos phi component also over here. Okay, so that you integrate with respect to like terms. I hope you understand what I'm saying. Please, is it understood?
No, sir. No, sir.
Okay. What I'm saying is, when we talk about the spherical coordinate system, our dv, okay, is always given by this, the expression we are having over here. Okay. But then knowing this as our dv, we want to find the v. Okay. Or better still, don't find the dv. Let's leave it just like that. But then we know our rho in that of the charge is given by, when we want to find the charge, we're only giving volume is given by this. Okay. Now the rho was given to you the question this form. Okay, this is the function or the density or for the charge within that volume we are dealing with. Okay. You said that V is in which coordinate system? It's in the spherical coordinate system. And the V, the spherical coordinate system, is given by what we have over here. Okay. So if the V is given by this, it's just a matter of.
You can never pull a strong woman down. She got it all within a swan. I was sorry. Very confident. She never wear proud.
Yanjaniana. Saka Yanjaniana.
So we have our row here, and we know that the V is also here. So we just put the row over here, then we also put the V over here. Is it clear?
So you see for him, I can of crying and
Yes,
chill.
sir.
Sir, row, and the map by our way to him. So one for that coupon, I want try as ya. Yabba, now you'll be a man reply.
No, but this one is not my job. It's math.
Eh, yanim sir, na
Integral.
edum bibiana. What Paquan buffer Saba try as ya. And then I'm who besides a crazy cry intimate in you, I don't know.
This is just formula work. It's very simple. I don't know why you are finding because he
Ah,
said
yes, simple, man.
the charge is good.
Yes, simple, man. Oh.
Mr.
Eh?
Yusuf,
So you
Yes.
see,
Mr. Yusuf,
Yes,
Yes.
simple, man.
so you see,
adwene wu, ya bre.
so you see.
Yes.
Yes. Perhaps maybe if we were to use a white border where whatever you are writing is clearer, maybe I think the understanding would have been there. I think that's
No,
a
but
difficult
what is
thing.
even writing is clear. But I say, yenti adina sintina yehuno.
You
What
are
is
not
writing is
getting.
clear.
Hello. Oh, you are.
Hey.
Mark.
You see,
I'm not a man
Mark.
can the
this is
background of
this
integration,
pure,
no, is not there.
this is pure
You get
calculus.
it. That is why I say, oh yeah, yenti minti asiano. Nti sɛ yɛbɛtumi
Anase
atena ase na ne ho atɔ no a
Mark Vota and Mark Sechi. Mumbremwe, calculus.
This is pure calculus. Oh.
I mean, this is purely formula work. Why?
Yeah.
Because we said the question said we should find the charge, right? And we stated earlier that the charge is given by the integral of that volume you are dealing with respect to the density of the charges given in that portion. Then the dV. Okay, and the question went ahead and said it's in the spherical coordinate system. And we said dV in the spherical coordinate system is given by what we have here. Okay, dV in the spherical coordinate system is this. Okay, sorry, we have square here. Okay, so if this dV, now let's substitute the dV here. And now the rho is also given here. So that we know our Q will be equal to, now we bring our integral sign. Now what is the rho? It's 5 cos
Squared
squared phi all over r exponent 4. Okay, times the dv, which is already, which is r squared sine theta dr d theta d phi. Okay, but we realize the differentiation we are having here is 3 times because you are differentiating respect to r, respect to theta, respect to phi. And hence this can't be just one, because if you are doing one, you are just integrating respect to only this, leaving the dr, I'm sorry, the theta and the phi. And hence you have to integrate 3 times so that we deal with that differential of this, that of the theta, and that of the phi.
So you can you take the differential maybe one at a time, slow, then it will be clear.
That's what I'm saying. It's mass. It's not
Uh-huh.
me to integrate this for you.
Maybe that
So
will
that
be the
fine,
clarity.
fine. Let's pay
Maybe
attention.
try. Let's
Let's pay
look
attention.
at it again.
Now you realize we have r squared here. We also, I'm sorry, r to the power 4, and you have r squared here. What I'm trying to do is I'm just grouping like terms. I'm not changing anything. Okay. Now the 5 here is constant. So let's bring that one out. So we have 5 outside, right? Now realize we have r to the power 4, r to the power 2. So when we multiply these two, what are you going to get? 1 over r squared, right?
Yes. Yes.
So we have r to the power 4 times r squared, right? And we have
Sir, please, are you writing?
here.
I
Sir, we are
can't
not
So
see.
seeing your write-ups.
you can see.
Yes.
please.
Your cursor is not moving.
Hey, is it only me or is it only Madam Felicia or you're all not seeing it?
I can't equally see. It's not moving.
It's static.
Hey, the thing that I'm writing is not moving.
No.
We cannot see it here.
Your cursor is just at one place.
Yes, no.
Is it moving now?
Bonsema
No.
Sakazani. Bonsema Sakazani. And now,
Sir,
Bernard,
no.
what's Sakazani?
So it's not moving.
And you may.
Let me stop
All right,
sharing.
it's moving now. It's okay. It's visible now.
Yeah, it has moved.
It's
So
visible
It
now.
has moved.
Also for Bernard, that's okay, Zani.
Has it moved now?
Yes,
because
now we
yes.
can see it. Obianso will be here.
Say one them at them.
Now why no
Yeah.
am kakra no?
So I said with this one, we are factorizing the 5 here out, and that's why we have it out because they are constant.
Okay.
Okay. Now we are grouping like terms. So if you take this whole thing, we have r to the power 4 and we have r squared. So we have 1 over r to the power 4 over here times the r squared, meaning from this equation, this one is out and this one is also out. Okay. Now let's put the integral sign over here for the first one so that we put the dr here because all what we are talking about here is respect to the r. So now this one is also out. I hope it's clear.
Yes, sir.
Yes, sir.
Okay. Now let's go to the second one. Let's integrate respect to theta. Now, if you are integrating respect to theta, realize you don't have any cos theta here. But I'm sorry, you don't have any theta here, but you have sin theta here. So you have sin theta. So this is also out. Now respect to what? The theta. So the theta is also out. I hope it's clear.
Yes, sir. So it's have to differ.
Then let's go to the next one, which is respect to the phi. So we have our next one here. And now the phi, we have cos squared phi. So we have our cos squared phi. Okay. So that now this is also out. And what is left? Our differ.
Differ.
Then also add the differ.
Okay.
Okay. After adding that, then we go on to the limit. We realize when we are doing this, we said the r, the limit is what? From 1 to 2. So the r can bring our 1 to 2 here. So 1, sorry, from 1 to 2. Okay. Then we move on to our theta. And we say for theta, the limit is where? 0 to pi. Okay. Then move on to for the phi. And we say the phi is always from 0 to
2 pi.
Half our 0 and half our 2 pi. Now, when we are done, we get to this point, this integration. Now, this can cancel this, giving us what? 1 over r squared. Okay. We have our integral of 2 and 1. Now, the 5 is still outside. Why? Because it's still a constant. Then we have our half. And go to the second one, which you have our sin theta. Now, if you integrate sin theta, I get what? negative cos theta.
Theta.
Okay. And the limit is pi and then 0. I hope you are clear. Then we go to the cos squared phi. If you integrate cos squared phi, what do you get?
Negative sign. That's and that make a bino. You're the funny,
Now we're three.
Yeah.
If you integrate cos squared phi, what do you get?
Funny, sir. And the by sign, and yet negative the by sign.
If you integrate cos squared phi, what do you get?
H Nabaka.
Don't tell me sine squared. It's not sine squared. It's 1 minus something. What is it?
Where is say Mark and say Buta?
Huh?
But you see,
Where is say Mark and Mark Sechi and Mark Buta?
I know that I've been able to bring it to this point. From this point going, it's up to you for you to get it. The integral aspect. So take note of it. Okay. I know it's Mr. Cash Rebecca say enter and yes, today. Now for your banner go and that's when one could do this and be they expect me to do consider you.
Say I've been
a student before. And you see we be because during my time I did Fourier series, beta and gamma functions, and it contained a lot series of this whole thing, about 10 steps before you arrive to the final answer. Lucky enough, the question I was solving, I knew the final answer just like this. It's me do baby, me skip almost 5 steps, and I'm sure therefore the answer is this. Kapani Baba me, I catch him so I'm full marks. Now, was escaping the integral aspect in your final answer. The rules, that's why and then escaping our final answer. Imagine say at the end of the day, you are not getting full marks. So please, it's up to you for you to go and do the integral aspects.
So why didn't they solve it in the model?
You said
This is the model. So why didn't they solve it?
You said it's the model.
So they should at least solve one, then we will follow the steps.
And I've solved it.
So it's not finished.
I'll break it down for you. Then you integrate respect to each direction. That's each factor. The R, the theta, and the phi. Now I've been able to do all that for you. And I was asking you, what is the integral for cos squared? This is not physics, it's purely math. The physics aspect is what I'm able to tell you that to find the charge, if you know the density, the charge density, then you also know what the rating at which you are talking about, which is the spherical coordinate system, which was given in the question. So now the physics aspect is that. That can be a math.
So it is.
Yes.
But also that can be a math. I didn't see a physics. I didn't hear physics.
Madam Felicia, you should understand, sir. Physics is related with EMAT. So definitely, EMAT, so as such, physics is all about maths.
It's all about maths. It's true.
So it behoves on us.
Physics is not really all about math, but the thing is, if you do physics, math becomes a bonus for you. But if you do math, physics is never a bonus for you. Because math is just like skeleton, and physics is skeleton, skeleton with skin.
Yeah, so with the flesh.
Give meaning to the answer to get in math. That's what physics is about. It is one matter. I wonder the integral aspect, the integration in there. I'll leave it for you. That one there, at least. I'll be
Don't worry, there. We'll write it for you.
Therefore, the answer is this: be a cashew. Why? That is it for that. Or we can move on to. There are more examples in here. but then I won't really bother with that. Then we can talk of also divergence. Haven't we spoke about divergence already?
Yes, we have talked about
That
divergence.
means we can skip this portion.
Yeah, the deaf and the kills. You have talked about them.
Okay. So basically, that's all what the divergence is also talking about. But this time around, we are trying to give a meaning with respect to what? Electric field. The electric field, what does it mean if you say you are having a divergence of a certain vector field? Okay, what is the implication? So you just want to tell us that within that field, how is the flux density coming out? Is it coming in a straight line, or as it's coming, then receiving the charge density is spreading out? And that's all what this point is talking about. I hope you are clear.
Yes,
Yes.
sir.
Yes, sir.
Okay, that's all what this portion is talking about. So there's nothing to spend more time here. Then we have some exercise. Let me see. Hi, Mr. Castro, so we there. What's of you in that? OBG. Vim. So we move on to. Oh, okay. We are now on session 3. We need to session 3. Okay. So we move on to work done in moving a point charge. Work done in moving a point charge. And likewise, we know what work done is about, right?
Course near any now, we need dim pa.
Uncle, you're for quantum mechanics near classical.
Mr. Ibrahim, course in the end, just say you need to activate your abstract thinking. I first told you earlier, say if you come to physics, open the courses that are more complex. This is one of them. I made it aware to you guys from the onset. So, normal. It's normal. And you won't want to can you be why? Okay, why you like it? Yeah, stress.
No integration. I saw you. I am an owner again.
That's how I was. What of you not needing she nay baby and yeah, the mobile name is I drew. I'm my kind of man.
Definitely find the other kind.
Yeah, the fans are quite now. And to say they come back though.
We do bonus. I know what kind of man up from here.
Community started in Contempa. Community.
One can be here. Ever know when you saw away. Yeah. Got to know what I
Let's
I'll
move
say
on.
I'm a
So when we talk about work done, I know you know what work done is. Basically, not in electricity and magnetism, but then basically when you talk about work, you know what it talks about. That's a movement of
The force, direction of the force.
Okay, so likewise, the same thing applies here. So when a force is being applied on a charge, right, for it to move from one point to another in a field of electricity or in the electric field, then it means you are talking about what? Work done. So a charge Q experiences the force F in an electric field E. In order to maintain the charge in a field, the force F must be applied in the opposite direction as same as this, so that if you want to maintain the charge in the equilibrium, that at this point, this FA must be the same as this F. Okay, so that at the end of the day, weight, their energy are all the same, or their intensity are all the same. So it keeps the charge at a halt or at an equilibrium. Okay. Now we define work. We define work. Electric field as the FADL, and FA is just the force that is experienced by the charge, and the DL is the direction or the distance through which the charge moves. Okay, and we said the charge is always given, the FA is given by negative QE, and the DL. And the DL, when we are dealing with the DL, we also have to deal about whether it's in the Cartesian the cylindrical or the spherical coordinate system. So if it's in the Cartesian system, it's QE dxi dyi plus dzi. If it's the have our the RE, the R d theta, then the Z. We have R d RE, the R d theta, A theta, and the R sine theta, the phi, A phi, in that of the spherical coordinate system as well. Now we have some work example here, and they say an electrostatic field is given, an electrostatic field is given by E is equal to x on 2 plus 2y, and the direction of I plus that of 2x in the direction of what? J. And the unit is what? Volts per meter. Volts per meter. Now find the work done in moving a point charge from Q negative 20 microcoulomb from the origin to 400 and B from 400 to 420. So it means at the first point you find the work done moving from the origin to this point, then the B from this point to the next point. And that's all this question is talking about. So how do you go back? How do you go about it? The first one is talking about 400. So if you look at the direction given here, which one is changing? Only the I or the S component, meaning the Y goes to 0. I hope you are with me. You are following what I'm saying.
Yes, sir. Yeah.
So in that case, we can eliminate this component. Why? Because this is the J component. The J component, Y is what? 0. Are we good?
Sir, you said we can eliminate which component?
The second one, the J component, because it's
Yeah, the J and the yes, the J and the K.
Yes, the E is given by S over 2 plus 2y. Okay.
Sir, please, are you writing?
Please, are you writing?
Yes, I'm writing.
Hey, we can see you.
Thank you.
Hey,
Yes, so mute. Yes, so mute.
is it showing now?
Mm.
No,
Sir,
please.
right and let's see. Yes,
Showing.
Can you see
it's not
now?
showing.
Okay. So the field is defined by the electric field intensity is given by S divided by 2 plus 2y in the I direction plus 2x in the J direction. And now the first one, the A is talking about 4I plus 0 plus 0. This is 0J and this is 0K. Okay. It means all these two components are 0. So our interest is only on the 4I. Why? Because it's really that one that have a component. And then this one goes to what? 0. You can need that one. I hope it's clear.
Yes, sir.
Okay. Now we said the work done, the W, is giving us negative Q E L. Okay. And if you look what is given here, you have I and J. So basically it's in the Cartesian coordinate system. Okay. So that now our Q, we substitute whatever you have here in the equation. So that our Q is what? Negative 20. So negative 20 times the negative we are having here gives us what? 20. That's why I have 20 might go over here. Okay. Now we have our integration of the S component because the Y component is 0 and the K component is 0. So we only have this in terms of X. So that it will be negative into bracket our Q is negative 20 micron. Okay. Then we pay attention to the S component because the Y is 0. So the S is S over 2 plus 2y. Now I times the SI, mean I dot I will go away. So you have what? Our DS. I hope it's clear.
Yes, sir.
Okay, so that this will give us 20 micron, right? Now we want to find the quantity. It means we have to integrate to get rid of the dx. Okay, by getting rid of the ds, we integrate it. Okay, now if you are integrating it, what is the limit? From the origin, means origin is 0, 0, 0. So from 0. And what is the limit that is moving to? The x, which is 4. Okay, then we put in our integral function, which is s on 2 plus 2y all ds. Please, do you understand to this point?
Yes, sir. I do understand.
Okay, so that now you have our, if you integrate this, what are you going to get? Then bring the 20 micron out first. Now, if we integrate s on 2, what do you get?
S square over 4.
S squared over 4. Okay, plus what of the second one?
2y.
2sy, because this is treated as constant. We're integrating respect to s, so the x will just multiply it. Then you get whatever you are dealing with. And the limit is where? From 0 to 4. Okay. So when you are done, you just put in the values of the s value. So wherever you have y is 0. So you put the 0 there. Mean this term goes to 0. Okay, then you put your 4 here. So you have 20 micron into brackets. You have 4 squared over 4, which is equal to what? May I try more?
20 times 4.
Eh?
20 times 4, which will be 80 microcoulombs.
And that's what you have over here. Is it clear?
Yes, sir.
Pacho, there was 4 squared. I don't know. Yeah, you see.
I say
20 times 4 means 4 squared. No, we didn't use it.
we use it. This is cancelled as square here, going away.
Okay.
Yeah, 4 squared is
Because 4 square is
4 times
16.
4 all over 4. So 1 4 will
16.
cancel the other 4. So we'll be left with
That's
only
what
1
I'm saying.
4 remaining.
Because
Okay.
4 times 4 is 16, and 16 divided by 4 will give you 4. So that I get all this 4.
Okay. Sorry, Matthias.
Okay. So that's for the A. Now the B is from this point to this point. Now it means when you are talking about the B, the S is from 4 into 4, telling us that the S component is now also 0.
Yes, it doesn't move.
The Y is what is moving from 0 to 2.
To 2, yes.
The Z is still 0, 0. So now our interest is really in the J direction. Okay, so that this time around, the E that is equal to S over 2 plus 2y or I plus 2x number. Yes, 2x j. Okay, this time around, all this also goes to 0 because the I direction is not moving. The only one moving is what? The j. So you consider only this aspect. I hope it's clear.
Yes, sir.
So if you are considering this aspect, our E will be equal to, oh, why is this math? Will be equal to 2 by J. Okay, so that when you integrate this, we are going to have our dl also in terms of the J direction is what? Where is it? The dy is what? Only the dy, because now the dx is 0, the z is also 0, so the dl is dy. Okay, so that this will be the w is equal to negative q, then our what is it? Q and our E dl. Okay, so that this is equal to our Q is still the same charge. It is 20 coulomb. It's negative 20, but this negative will cancel it out. Now our E is 2y. Then our dl is what? Our dl is dy. Okay, so that at the end of the day, this one is also moving from where? From 0 to 2. So that when we integrate this, we are going to get 20, the integral of 0 to 2 of 2y dy. Okay, so that at the end of the day, this will be equal to what? 20 into brackets. Now, if you integrate 2, what do you get?
Y square.
Yes, so 2y squared on 2. Let this cancel this. Madam Felicia, one thing I may you. So that this will be equal to 20 into brackets y squared with the limit of 0 to 2. So that at the end of the day, where you see the y, you put the 2 there. So this will be equal to 20 into brackets 2 squared. And we know 2 squared is what? 4. So that 4 times 20 will also give us what? 80. Is that clear?
Yes, sir.
Okay, and that's all what you need to do. I just wanted to explain it to you. Don't go and understand it. Okay. Then go to conservative property of the electrostatic field. Now, the work done in moving a point charge from one location B to another A in a static electric field is independent on the path taken. That's in terms of figure 3.2. Now, they are telling us that for conservative property, you don't really care about the path. It's path independent. To be able for this part, I could go. For this part, I could go. I don't really, you don't really care about the path. And this is what was in Unit 1, Section 6. What I asked you guys to read. This is all what it's talking about. It talks about a conservative force field. So if you understand that one, there's no need to stress myself over here. Can move on. Then go to electric potential between 2 points. Electric potential between 2 points. So if you are talking about electric potential, we are just talking about the work needed to move one charge from one point to another point. So with respect to B and A, we are referring to the electric potential needed to move a charge from point A to point B. And that's all what this also talks about. And as I said, when you are talking about electric force field or electric field intensity, it's always a conservative force field, meaning you don't really care about the field and the path. It's path independent. Okay. So that is also that. Then talk about potential at a point charge. So as you see, when you are talking about electric potential difference is different from potential at a point or potential of a point charge. So electric potential between 2 points talks about the potentials moving 1 point to another point, right? But the electric potential is just talking about the potential of electric charge with respect to infinity. With this one, you don't have any charge that you are giving reference to. So it's always the work done in moving a unit charge from infinity to a region of electric field. Am I making sense? If you are dealing with electric potential, we are talking about the work done moving a charge from infinity to a region of electric field. But if you are talking about potential difference between 2 point charges, we are talking about the work done moving electric charge from 1 point to the another point. I hope the difference has been established.
Yes, sir. Yes. As for this one, even yesterday we did it. So
okay. So you can move on. No. Then move on to relationship between electric field intensity and electric potential. And it's not something strange. We know you can put it in this form. You are not wrong. But then there's a way by going by it. I don't know. I think those who did the electricity and magnetism, I taught them this. I guess. Madam Fisher. Okay. So we all know that from Coulombic force, F is giving, electric field intensity is given by what? K Q over R squared, right? That's electric field intensity is given by this. Likewise, electric potential is given by K Q over R. Okay, so these are the relationship between the two. So that if you take E, okay, so that if you take E, okay, you can write it as K Q over R all times 1 over R. You've not made any changes because if you multiply this to this, you are going to get back this. But we know what we have here. The first term here is the same as the V, so that E can be equal to V times 1 over R. And hence, V is equal to E R. I hope it's clear. And that's the same thing we have over here. There's no difference. So if you are asked to state the relationship between them or to prove it, you can go by either this or that. You are not wrong. It's correct. I hope you are good.
Yes, sir.
Okay. So you can move on to we have some work examples here. I'm not talking about the exercise because they are all objective questions. And you know what that means. So obviously on him what it means. Did someone say something?
no.
Oh, okay. So you know
What does it mean? What does it mean?
Oh, it means one care. It won't count.
I do not count.
The other now was three. Is a classroom when you had you other.
It simply means we can solve it on our own. Simple.
That's it, Madam Fisher. I like that.
You solve it quick.
We can solve it on our own.
For the work examples, that is the long term, but for a idiot, for the objective there. So we understand, don't worry, we understand, we solve it on our own.
And please take note. I think your first quiz is from unit 1 and unit 2. So make sure the exercises, the objective exercises at that point or you solve everything.
Yeah. So unit 1 and unit 2, let me write it. Unit 1.
Hey, Mr. George, make us all the already and come po.
It says, sir.
And you're very say, in Gramon to will be rubbing to. Okay. So that is that. Then go to section 4, which talks about electric dipole, flux lines, and electric density electric field lines. So you see, apart from the unit 1, which was more complex than that, the other things are stuff that we've done before. Okay, that's why I don't want to stress myself. Now, when you talk about dipole, what is dipole? Dipole just talks about charges, opposite charges with the same magnitude, but opposite charges. Okay, so a positive and negative charge with a very short distance between them with the same magnitude at each point. Okay, and because these charges are having opposite charges, they are attracting each other. So assume we have a line, right, a straight line that is at the midpoint, and on that line we want to find the impact of the force at each point. That means we are dealing with what? Electric dipole moment, and that's what this also talks about. So if you see here, you have the positive charge, you have the negative charge here, and separated by the distance d. But mind you, the charge magnitude of this charge is same as this charge. So if this is 5, means this is also 5. The only difference is this is a negative charge, this is a positive charge. And now assume we have a point here, right? And want to find the impact of which these two forces are having at this point. That means we are trying to solve for the dipole moment of this system. I hope you agree.
Yes, sir.
Okay, so that is also that for there, which I won't stress you. But then note that if you are talking about the dipole, this is how you go by it. Okay, I don't want to stress myself by taking you through all the derivation. Because even semi-proven crowd won't say I said no financial. But then know the definition for a dipole and know what a dipole means. Like if you are talking about a system of dipole, you should understand it. That's the basic thing. If you talk about a dipole, we are talking about two charges with opposite charges, right? But the same magnitude, separated by a very short distance. And within this system, the charge or the force field or the intensity felt at any given point, then we are dealing with what? A dipole system or a dipole moment. Okay. Then we can move on to flux lines. Flux lines, and as you know, when we are talking about flux lines, is it the same as talking about electric flux? But this time around, our interest is on the lines that is moving. Interest in the lines that are moving. And if you talk about flux lines, we can eliminate what we call equipotential surface. Potential surface. Then who has an idea what equipotential surface is? It's an English word. Though.
Equipotential.
Yes.
Equity say equation. So talking about
So it is equal potential. Equal.
Yes, equal potential. Okay. So assuming we have a surface like this, and we say this surface is an equipotential surface. It's like saying it's a Gaussian surface. Why? Because the only difference between these Gaussian surfaces, when you are talking about Gaussian surface, you are talking about charges and flux. But then when you are talking about potentials, we are talking about potential. Okay. So that the electric potential at this point is the same as what is over here. The same as what is over here. Okay, so within this surface, the potential at any point is the same. And I said it's similar to Gaussian surface because against Gaussian surface, the charge here is the same as what here is the same as whatever at any point. Okay. So if you are talking about a potential surface, it talks about the potential at the surface at each point is always the same. Okay. And now if you are dealing with the work done on a potential surface, it's always equal to 0. It's always equal to 0. Why are we saying that? Because say the potential at here is the same as here. So it means we don't need any work for it to move from this point to this point. Okay, we don't have to push it or you don't have to apply anything for can move from this point to this point because what is over here is the same as what is over here. So there is no need for you to find the potential difference between them. I hope it's clear. I hope it's clear.
Yes,
Yes, sir.
please.
And that is what is defined here. Okay, so for equipotential surface, always the work done is equal to 0, or the work done is equal to 0. Okay. Now let's take these flux lines and this equipotential surface. Realize we first have this equipotential surface. Okay, means any charge situated within this region is the same. But we also know that the further you are moving away from the charge, the lesser the intensity you are feeling, right? So at this point, the intensity felt is very high. So the potential surface within the first circle is higher as compared to the one that is being felt at this region. At this region. Okay. Likewise, the potential felt at that point is also higher as compared to the outermost region, that's this region. Okay. So assuming we call the inside one, let's say 1, and call the second one 2, and the outer one 3, then means the potentials at 1 is greater than the potentials at 2. And the potential at 2 is also greater than the potential at 3. Okay. And hence, all charges or the field or the potentials felt within every region at this point is the same. Likewise, if you come here, all the potentials felt within this side is the same. When we go to the third region, the same thing applies. I hope we are good.
Yes, sir.
Okay. Please a minute. Hello. Yes. Hello. Hello. Oh.
Yes, sir.
Okay. So if you take the second one, right? The second
Yes.
diagram over here, we can see we have 2 flat lines, right? One moving this way and this moving this way. We have a point where they are all intersection. Okay, a point of intersection between them. Okay, and we are talking about the potentials at each point. So if you look at this region and this region, please a minute. Hello? Yes. Yes, please. Yes, I'm listening, please. Registration for what? What registration are you talking about here? Yeah, hello. Hello.
Hi.
Yeah, sorry about that.
No
Now, if you
problem,
look
sir.
at these 2 points, right, we have a point here and also have another point here, okay. And we have another region here and we have another region here. So assuming we are talking about this intersection and let's say this point, at which point do we think we have a very high potentials? Okay,
Sir, come
let me
again.
label this. Let me label
Yes.
them. Assume this is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. So within this surface, where do we have a very high potential?
At 1.
1 and 2.
1 and 2. Let me bring this here at 7. Where do we have very high potentials?
As I'll still say 1.
What? Who else?
I'll go for 1 and 2.
Obi will different answer apart from that. Okay. So where we have a higher potential is 1, 7, and 2. That's this region. Why? Because that's where we have intersections of all the flow lines coming in there. Okay. We have the intersection of the impact of this, that of this, that of that, and that of this one as well, as compared to the outer ones. Okay, because the closer you are to where all the points are intersection, the higher the quantity or the magnitude of that field is. Because you also talk about the point that as you are moving further from the surface or from the region, the lesser the force you have on you. And that's why sometimes if nsuo na say where you say to go baby it's quite better for no one to get closer to that perimeter because have a range at which the intensity is very high. But then as you're moving further, then the intensity is reducing. Okay, so if you look at what you have here, you have the intensity higher at the point where they are all intersection or they are all meet. Okay, but as they are moving away to their respective directions, then the intensity is also reducing. Okay. So you can also talk about that. Then talk about dipole moments, which I won't. Dipole moments, yes, we have already talked about that, but then I won't really stress myself on that. Then we can go on to
Energy density in electrostatic fields.
I don't want to stress yourself, likewise myself on that. But please, the fact that I didn't mention them doesn't mean you shouldn't solve the objective questions. Take note.
Okay.
All right. You can move on to the current density and conductors. Current density and conductors, of which this one we've done before. Or you didn't do it when you're doing electricity and magnetism. Please, did you do it?
No, sir.
Yeah, we
We
did
didn't.
it. We did it.
Are you
You
sure?
did it.
Yes, conductors. Conductors, we did conductor, insulators,
Which
and
one is current
semiconductors.
density and conductors? You
Current density.
and conductors.
For current density, I don't think we have done current density.
Okay, but then you know what current is, right?
Yeah.
The rate at which charges move with respect to time.
Yes.
So the current in a wire is the charge per unit time passing a given point. By definition, negative charges moving to the left count the same as the positive ones to the right. This conveniently reflects the physical fact that almost all phenomena involving moving charges depends on the product of the charge and velocity. In practice, it is ordinarily the negative charge electrons that do the moving in the direction opposite to the current. Current is measured in coulombs per second or ampere. And mathematically, current is given by the Q dt, where the dq is talking about the charge and the dt is the respect to time. Then thus a current of 1 ampere charge is being transferred at a rate of 1 coulomb per second, where current density J crosses a surface area as shown in figure below. So if you are the figure, so now a current is just should I say in one-dimensional space, or in one-dimensional space. But if you are talking about current density, you are talking about a bulk current moving through a cross-sectional area. I don't know if I'm confusing you or you are getting what I'm trying to say. Are you guys there?
Sir, confusion. Sir, confusion.
They're here.
Confusion. Okay. Take it this way. Okay. We have our X, Y, and Z. Okay. So if you are dealing with current, we talk about it, the movement of charges at a given time, right? And if you talk about current density, our machine go, oh, take care, or you just they need the machine. My mouse is not even moving, it's just freezing. Oh.
Hello.
Yes.
Mintishe mikaze me end.
I'll be until or call of Kakra.
Hello.
Hi.
My network
Yeah.
and my net messing up with me. That's why I've been off for a while. Yes, so as I said, if you are talking about current, you are just talking about the rate at which a charge moves. But if you are talking about current density, as we all know, if you talk about density, we are talking about the rate at which something is moving with respect to the cross-sectional area, right? So we are dealing with the current that crosses a particular surface. Okay. And hence you can get the current, right, from a current density. So assuming we have a whole lot of current moving through a surface area and want to know, so the current density moving or crossing a surface area, you want to know the current at each particular point. You can also do that. You have an equation 5.3. Okay, meaning we integrate the current density with respect to the surface area. That's what we are dealing with, the current that we are looking for. I hope it's clear. So what I mean is with this diagram, assuming we have a current density passing through all the surface, right? You want to know the current at each given point. It means you can take a unit of this density, right? You can take a portion and we just integrate. Likewise, like the surface we have over here. We find the current at this given surface. When we get the current moving at this surface, then we can find the total across the entire surface. Is it clear?
Yes, sir.
Yes, sir.
Okay. And we said to find that is given by equation 5.3, that the current is given by the integral of the cross surface we are talking about with respect to the current density that we differentiate with respect to the surface. And that will give us the current. And now they said we find the current in the circular wire shown in the figure. If the current density is given by 50 into bracket 1 minus exponential of -1000 in the z direction or the k direction, as shown in figure 5.2 below. The radius of wire is 2 millimeters. So now they're giving you the area, I'm sorry, the radius. They're giving you the radius. And now this is it. So the current is moving in this direction, that's the z direction. And now the surface that we are talking about is what is given in this small region here. Okay. And they say you should find the current passing through the surface. And now this entire area is the current density. Okay, so at this point, what will be the current moving? Just we are this small region. And that's what the question is just asking. So you just integrate the function that was given to you with respect to what r and then your far. Okay, because you are dealing with what? A cross-sectional area. Let's talk about what? We talked about what? We are talking about a wire, right? A circular wire. So obviously we are talking about a cylindrical coordinate system. So if in the cylindrical coordinate system, what is our S in the Z direction? Or the Z in the Z direction is out the far. I mean the S in the far direction, the cylindrical coordinate system.
Sir, are you writing?
Yes. It's been
You're
by.
not seeing it too. You're not seeing it.
Let's see.
You are not seeing it.
Musa.
I'm coming. Let me check again. My network is messing with me today. Is it still not showing?
Are you still writing?
No, of course. I want to see whether what I wrote has come or
Oh,
something.
yeah, no, it's not showing.
Wow. The network is making us up this evening. Let me. Has it come now?
No, please.
Okay, you let me share it and share it back again and see if it's going to come now. Is it showing now?
No, sir. No, sir.
I don't know why. Please, my network is not giving me the chance. I don't know. Maybe I don't know if we can end here today, and maybe we continue. If you'll be free tomorrow, then we continue from there. But what do you guys think? Because I'm trying to share, it's not even giving me the permission to share. Mr. Castro.
Yes, sir. Unfortunately for tomorrow, we have scheduled a time with our PCK lecturer, but I don't know whether he will make it or not. If he's not able to make it, then I'll let you. But I think we can also schedule it for Friday too, if that can be the case. But I have to talk with my colleagues about it if they'll be free on Friday.
Okay, sure. Because we still have, I think with this one, we are almost done with the Unit 2. So I want us to finish with at least Unit 3 before, not tomorrow, but if you are able to finish with Unit 3 by Saturday. I'm sorry, Sunday. Sunday. So that on Wednesday we do the Unit 4, then we just get our hands off this thing.
Okay, sir.
All right.
I think I am there.
But you say next week, because you say a practical week on.
Our practical, this our practical here.
Maybe just say a practical week. Is that a person on Tuesday?
No. But we don't have practical. If we have practical, then it's practical week. But I don't have any practical, so it's not practical week.
Chemistry for practical.
But we are not having practical. And I want to say, yeah, the any practical, and the practical week in my. For others, it will be practical week for them, but for us, it's not practical week.
That's what you want you to clarify.
We don't have.
No, we don't have anything.
Okay, thank you.
That is, I said, yeah, Kobate, and Yama, Anya, say, you bit mask, do ya in Bakwash, or one of the days, still be
Yes, yes, we can do that. Definitely, we can do that. With my sir.
Okay. And I guess we can call it a day.
Okay, sir.
All right.
Thank you, sir, and have a wonderful evening.
All right. You too.
I had done a dream, who be why?
What's it?
I had done a Kai be
What's it?
I had Kai be in Ejinaquano.
Oh, cool. I want for Martin to wait me.
Yati, inshallah.